you see it? Can you see the
Thank you.
slides?
Thank you.
Okay, so I suppose everyone can see the slides.
Yeah.
To begin with, I want to thank the 6 organizers for putting together this marvelous conference. And special thanks go to the 2 Yuris and Oleg. And I also want to use the opportunity to say happy birthday, Rafail Z. 90th birthday it's a great milestone. Professor Rafail Khasminskii has made fundamental and lasting contributions in many areas of probability and statistics. I was not his student, but I have had the privilege working with him for more than 20 years. I just look at the math review. I found we actually wrote about 14 papers together, according to the math review, maybe even more than that. So I have learned a great deal from him. I remember the first thing we started was a friend of mine and myself was trying to work on manufacturing, flexible manufacturing systems. Mathematically, the problem we need to deal with is actually a continuous time Markov chain, but in a way singularly perturbed. So there's some, difficult point to handle when you are close to the boundary layer. So we talked with Rafail. He suggested a very nice approach by using singular perturbation. So that started the work in that direction. Later on, I worked with him on, densities of a singularly perturbed diffusion and the 2-time scales. And also, I know the next speaker will be George Papanicolaou. We also look at his 2-time scale with circular term, which is another term we need to average out. In addition, we worked on something like no recurrent diffusions. I think the last paper we worked on was together with a former student of mine, who is now Chao Zhu, who is now a professor at Wisconsin, Milwaukee. So that was on stability of the switching diffusion system. In the process of studying that, we actually Rafail talked to Collier, and he suggested the book of Lieberman for systems. Well, anyway, the story goes on now. And in addition, I would like to say during the years, we have become very good friends, and I attended many parties at Rafael's home. And I learned from him how to be a good person, among other things. Anyway, so let me begin my talk. Let's see. So anyway, I moved to Connecticut recently, last year, actually. So rather than talk about this Kolmogorov system in general, what I'm going to do is to look through one example, which is the so-called SIR model. We will see what that is when we get to that point. So the talk consists of the following 3 things. I'll begin with the motivation, why we want to study the problem. And then we'll talk about the particular example. And finally, I'll close the talk with some current and future efforts. I would mention that during the talk, you will see the influence of Rafail as well. So, so why we want to study Kolmogorov system? Well, this is really a long-standing question in math biology. So people ask the question, what is the minimal condition? Meaning necessary and sufficient condition for long-term persistence of a population or for long-term coexistence of interacting species. All right, so naturally you have this for stochastic system, before you have that for deterministic system as well. So by the way, the work I'm going to report actually is a joint work with a number of people, including Dang Nguyen, two colleagues from Vietnam, and the last one, Professor Zhu, is more senior. All right, so by homograph system, what I'm looking at here is I'm starting with autonomous nonlinear differential equation. So you have n populations, x1 through xn. Now you have the ordinary differential equation given by this equation. Now this is what is called a homograph system. Well, we can certainly add noise to that because we are doing probability and the stochastic processes. And also it is very easy to visualize in two-dimensional system. So I'm looking at the two-dimensional system and add noise to it. So I have the B1 and B2, both of them are Brownian motions. Well, they can be independent or not, is not essential here. And while we all know a special linear case would be the geometric Brownian motion model, which is used widely in math finance. Now, you ask the question, what is essential in studying this kind of system? So in particular, I'm looking at this so-called logistic equation. We teach that in the sophomore calculus class or differential equation class. So here, the R is what we call the growth rate, and the K is another parameter. Now, if you put in noise, if you have a Brownian motion put in, then you ask the question, what is the corresponding growth rate for this case? It turns out, in this case, the growth rate is no longer R itself, but it's R minus sigma squared. That has been studied by many people, including in Rafail's book on stability. So you know that if lambda is less than 0, then the population goes extinct because that's really asymptotically stable. If that one is greater than 0, then the population is persistent. In the sense, it converges to its unique invariant probability measure. The critical case is the one when the lambda is equal to 0. We call that critical case. Actually, in Rafail's book, he termed that as a no recurrent diffusion. All right, so what about the literature? So let me give you something, a quick review on that. For this kind of system, of course, we can mention the work of Lotka and Vatera in the 1920s for the so-called Lotka-Vatera model, dealing with a rabbit and a fox, predator prey and all other kind of variation. And then around the 1920s, Kermack and McKendrick actually started looking at the so-called SIR model for infectious disease. By the way, for the Lotka-Vatera model, I'd like to mention the work of Rafail and Robert Lipser and also Fema Kleppner. In the 2000, they have several papers in that area. Now, in 1938, the logistic model was done by Verhulst. And fast forward to the 90s, we see a lot of people got interested in the so-called replicator dynamics that include Rafail and also his former student. Now, then in the 2000, from 2000 on, many people actually in dynamic systems and mass biology actually got interested in the problem, including Michel Benham, Schreiber, Evans, and colleagues, and many others. So there's quite a bit of a significant development. How we got interested in the problem is that starting from 2016, actually the paper was written 3 years ago before that. So here I highlighted the several things we used to treat such models. So we used the intuition from dynamic system theory to examine the boundary. Later on, we'll see that. And we identified the threshold because it's the growth factor or growth rate. And then we treated degenerate diffusion and we characterized the support of that. So initially we look at basically just two-dimensional problem because as I mentioned, it's easier to visualize. And later on, we worked with Henning, and he was actually a student of Evans, and he was a postdoc at Oxford at that time. So the problem was generalized to SDEs living in n-dimensional space. Well, the first quadrant basically is non-negative solutions. Now, a significant development I would like to mention is the work by Henning and my former student, Nguyen, that they treated the general Kolmogorov diffusions, gave a complete characterization. Now, our recent work actually dealt with functional Kolmogorov systems. We indeed gave a complete characterization that we used the idea of Dupaire's functional Ito formula and the idea from Martin Hare's asymptotic coupling and dynamic systems approach, and so on and so forth. So before going any further, let me mention what I mean by stochastically persistent and extinction. So I'm looking at only two-dimensional system because, as I mentioned, it's easier to visualize in this way. Now, we say that xt is stochastically persistent if it is bounded above and below with positive probability. Actually, the probability is close to 1. And you take the inf of that. Likewise, you do this for y. Now, if both x and y persist, then the system is said to be persistent. Now, what about the extinction? Well, for extinction, you only need to have one of them. The definition is this. If the limit xt goes to 0 with positive probability, you don't have to have this one close to 1, just positive probability. That's extinction. All right. So an important question for people, especially in mass biology, is the following. What conditions, it's a type of what conditions, or what condition is the system, and what condition is the system persistent? And if the system is not persistent, what species persist and what species go extinct? So now recently, this problem has attracted much attention. If you look at the internet, you will see many papers were written, but some of them are not as, the conditions are not as sharp as desired, and only sufficient for extinction or persistence. So the main idea is to choose a function that imposes conditions on the function so that the function has some good property. Then the results obtained for the persistence and extinction actually is based on the function chosen. So this will not reflect the true nature or the coefficients of the dynamic system. So with the short introduction, let me go to the second part, which is example of a homograph system. So I'm going to look at the SIR model. Well, it's a conference, but I couldn't help to do a little bit of digression to mention the name Ronald Ross, who was quite interesting person. He was the first Nobel laureate of UK. He was also the first Nobel laureate of UK born outside of Europe. So he was really a polymath. He was a genius in his early age. He liked math, he liked poetry, he liked music. When he was 14, he wrote a math book. And later on, but anyway, he was the eldest son of the 10 children in his family. His father, however, wanted him to be a physician. So he fulfilled the duty. And later on, he was sent to India. Over there, he discovered, the malaria transmission, epidemic transmission thing. And then I should say at the same time, there was a contemporary person, Giovanni Grassi. His work on malaria, in fact, is more directly relevant to human transmission or health. So both of them were nominated for Nobel Prize. Actually, they had a pretty big fight. But the mediator named Koch was very much in favor of Ross. So Ross got the Nobel Prize, but Grassi didn't. Anyway, so that's a little bit of the digression. I hope you don't mind with that. So building on the research of Ross and Hudson, Kermick and Kendrick actually wrote 3 papers, commonly referred as a trilogy, published in the UK, the Royal Society Journal. And later, their work was reprinted in early 90s in Bulletin of, I think, Mass Biology. So what is the idea here? Basically, as I mentioned, is a continuation of the work of Ross on the infectious disease, but they divide the homogeneous class into 3 families. So this is the so-called compartment model. So one part is so-called susceptible class. The second one is the infected class. And the third one is removed class. So now even for modeling the COVID-19, you will see some people are using some form of SIR model. So the SIR model they are talking about, or they are formulating here, is that once you recover you are permanently immune. This certainly not apply to the COVID-19, but there are variation of the SIR model, like SIRS and so on and so forth. I will not be able to get into that part. Anyway, so we would be interested in what is the mathematically you describe this. What is an ordinary differential equation? Is a system of them, where S is apparently the susceptible, I is the infected, R is the removed. Now you have a bunch of parameters. For example, R is the per capita birth rate of the population. Beta is the effective per capita contact rate. And the mu and the rho are the, the death rate corresponding to disease-free and the disease death rate. Anyway, so we have this. Now, you wonder for such system, do we, apparently this is the Kolmogorov system, as we mentioned before. All right, so for this system, what we know, for the deterministic model, actually, people found a threshold. We call that lambda d. I use the lambda d to denote that this is deterministic system. So lambda d is completely given by the parameter. You see here, I have alpha, beta, mu, rho, and gamma, and so on and so forth. So now, you see this threshold actually is given by this. Now, if this one is less than or equal to 0, then the population tends to the disease-free equilibrium. Okay, so you have this. So the infected class in the long run becomes 0. The removed class becomes 0. Now, if lambda d is greater than 0, however, the population goes to an endemic equilibrium. Okay, so this is how they classify the deterministic model. Now, what is interesting for people working in stochastic processes would be like, what you do when you have a typical stochastic SIR model. So I wrote down the equation like this. We have a 3 Brownian motions, B1, B2, and B3. Initially, let's assume that B1, B2, and B3 are mutually independent Brownian motions. Sigma 1, sigma 2, and sigma 3 are the intensities of the white noises. Now, in reality, we realize that the environment is the same. So environment, I mean temperature, humidity, pollution, and so on and so forth. So as a result, you see, it's more reasonable to assume instead of 3 different Brownian motion, let's assume only 1 Brownian motion. Affect all 3 classes: susceptible, infected, and removed. Well, this simplifies the writing. However, it complicates the matter because now, as you can see, the diffusion becomes degenerate because of the same Brownian motion use. The matrix is degenerate. So one of the important questions we want to answer here is to say, can you classify the permanence and the extinction of the disease? So what we want to do is we want to derive a sufficient and almost necessary condition. By that, I mean leave out the critical case. Now we realize that the removed class is not so essential in terms of studying the asymptotics. So we look at only the coupled system S and I. Now, how do we study that? So first, we have to make sure there is a unique solution. In fact, we can use the standard argument in stochastic differential equation. And for example, like Rafail's result, we can say we can actually show there is a unique global solution. Not only that, but also we know that the solution, in fact, belongs to the positive quadrant. This is because of the fact S and I, the physical meaning of that. And now, how do we analyze this? Well, to analyze that, to get the threshold like lambda we want to get, what I would like to do is we actually look at the boundary. This is the idea coming from the dynamic system idea. So basically, what do I mean by look at the boundary? Now, look at the first equation only. Now, if you set I equal to 0 here, you get a differential equation SDE of the following sort. So it's still susceptible class, but we use a hat because no I involved. So what do you know about this process? Well, for this one, you can solve the corresponding homograph forward equation. You get the invariant measure associated with that. The invariant measure actually has a density. Well, those parameters are given by the parameters in the SIR model. So, all right, not only that, but also we have a law of large number type of thing. If I integrate S hat and divide by T, let T go to 0, then you see this is just the average of that. By the way, this F star turns out to be the inverse gamma distribution density, which is nice. And in this case, we can also know what the expectation is, or what is the mean of this. It's alpha over mu. All right. So now we want to look at the growth rate. Now, what we claim is that the threshold, in fact, is equal to this minus sigma squared 2 over 2. Well, why this? Well, if you can recall when we talk about the logistic model, that's exactly the same kind of meaning. So if you use the lambda d obtained in the deterministic system, you see this lambda d is in the deterministic case. So we just add or subtract the sigma squared over 2 to it. So what is this? What is this lambda coming from? It's actually the Lyapunov exponent of IT. So how do we get the Lyapunov exponent of IT? Well, we simply integrate I and they divide by T, we send T to infinity. So now here I have 3 terms, the blue term and this and that term. The first term, and when T goes to infinity, goes to 0, because this one just a constant. The second one goes to 0 by the law of large number, or if you want to use Lipser's local martingale idea, you can also show that. So now we can concentrate on the third term. For the third term, recall that T is large and I is close to 0, it's small. So in that case, S is close to S hat. So I'm waving my hand argument saying this is approximately equal to that. All of those can be proved, but this one gives us good indication why this should be true. So if I'm looking at the integral here, I see the first one, I have the law of large number that gives me alpha times beta over mu. Now the last part is, the quantity we look at. Altogether, that gives us the lambda. All right, so that says log IT over T is close to lambda. Of course, when lambda is less than 0, IT goes to 0 exponentially fast. So, so the disease will disappear. So that allows me to present the first result, which says if lambda is less than 0, then the infected class will go to 0 with probability 1. And well, the susceptible class will converge quickly to the unique invariant probability mu star, where the mu star has a density F star, which is the inverse gamma density. So that tells us the distinction of extinction and so on and so forth. All right, so now let's look at one simple example or simulation result. I put in some parameter, alpha, beta, mu. You don't have to worry about the number, but what is essential is lambda is less than 0. Now in this case, then you see this one shows the picture of ST, the susceptible class, whereas the right-hand side shows the trajectory of IT. So IT goes to 0 exponentially fast, in fact. And so this picture shows the empirical density of ST and also, or the density of F star, and also the theoretical result of FT when F is the gamma distribution. So when lambda is greater than 0, we show that ST and IT together has an invariant probability measure. So I think I have to speed up somewhat. So now here we use the idea of support from Stroop and Vardan's work. So how do we find the support? Actually, we use the geometric control theory. The control theory becomes useful here. So basically, we need to verify something called a Homenders condition or Reshevsky-Shao-Homenders condition. So I will skip part of that. So this is the geometric control part, no stochastic involved, but it's a control system. So anyway, to make a long story short, we can identify this, this support, and we get a result. What is happening now is the joint process ST and IT, the transition probability converges to a invariant measure in total variation norm. The convergence rate is no longer exponential because you only have a sector as a support in general. So it's polynomial. All right, so another simulation result. So the two pictures shows the component of S and I, whereas this one shows the support. The picture on the left shows the support of the invariant probability, whereas the right side shows the distribution of the invariant measure. So my time is pretty much up, but I would like to say here we treated the degenerate case, but we can also treat it non-degenerate case. We can also add switching to it, switching diffusion instead of diffusion itself. So I'm pretty much out of my time. I just want to say our current and the future efforts include looking at the stochastic delay systems, stochastic partial differential equation models, and so on and so forth. So thank you for your attention. My last slide is actually just say, congratulations, Rafail, many happy returns. We cannot get together now, but I wish to make a virtual toast. Many happy returns, Rafail. Thank you very much.
Thank you very much, George, for interesting talk. And unfortunately, we have no time for questions. And our next speaker is George Papanikolaou from the Stanford University. He'll talk about robust denoise in imaging.